Today we discuss lines and planes. We begin with lines in R2, and this is something everyone has seen. In particular, we have seen slope-intercept form. We have seen point-slope form. And it's likely you've seen this standard form. It's a little bit more general because if you have, for instance, a vertical line, x equals 5 or x equals 10, something like this, the slope is undefined, and so you can't write the equation of that line in either one of these two, but you can in this standard form. Now, today, we're going to have two more forms for the equation of a line, and we'll begin with R2, and then we'll move into R3, where we do lines, but we also will have equations of planes in R3. Okay, so let's begin with an example where we find all of these. We know any two distinct points in the plane, there's a unique line between them, and this is true in Rn. If you have two distinct points in Rn, there's a unique line between them, and I have drawn the line here for P and Q. Okay, well, maybe I'll begin with point slope. That's the easiest for me to find. I have 2 points. I need to calculate a slope, and then I can go into this form, and then I will get the other two as well. So the slope of this line, we take, let's see, y2 minus y1 over, let's see, x2 minus x1, like this. We get 2 over 3. And then, for instance, if we want the point slope form, we can really use either point. I'm going to use y minus 1 is m, would be x plus 1. So here is one form of the line. From here, I can get the slope-intercept form fairly simply. I just multiply through, solve for y. I get y is 2/3 x plus 2/3 plus 1, or y is 2/3 x plus 5/3. Here is the second form here for this equation of the line. But then to get standard form, all I really need to do is subtract y from both sides. But personally, me, if I can avoid fractions, I do. So I'll multiply through by 3 at the same time. Okay, so I could get that 2x plus, minus 3y plus 5. Now I put my equals is 0. All I did is I mentioned subtract y, you get 0, but I wrote it on this side and then multiply through by 3. So this is the standard form. So here are our 1, 2, 3 forms. As we see, 3 forms at the top. Okay, now, but we are beginning our discussion of vector calculus and vectors, so we would like to think about vectors here. Up here, I will write a general statement. If P, Q are points on a line, then this vector V here is parallel to the line. And this is what I have drawn below here. Here is PQ. Now, in this part, let's calculate it for this example. What is V, this PQ vector? Well, if you remember, and we have practiced this, we take each entry of Q and subtract the entries of P. Okay. So this would be 3 minus 1 would be this entry, and 2 minus 1 would go here. This is 3, 2. Okay, so this vector, well, as I have drawn it, it sits in L, but we know the same vector could be drawn starting at the origin, and that's where we get this parallel to the line. Okay, now what else because there's something really neat happening here. We know every point in, well, R2 here, we can think about as either a point in the plane or a vector coming from the origin and ending at the point. So if I do this, okay, what happens when I take this red vector and add? So notice here, so in this example, if I take this plus this vector v, okay, well, this plus this, I get exactly the point Q. Now you can either see it looking at arrows or you can see it adding components. Now, this is going to allow us to write everything on the line in vector form because we take, okay, this vector, minus 1, 1, but now instead of adding the vector v, I can take some multiple of v. First of all, let's think about positive multiples. So I take this, minus 1, 1. I add positive multiples of v, and this is going to fill out all up here, right? You're going to get all of this part of the line, but then if I take negative multiples of v, so I still start with minus 1, 1, I take negative multiples of this, I will fill out all this part of the line. So in fact, you can write every point on the line, and again, I think about the point as being a point and a vector, kind of at the same time in this discussion, but you can think about it as minus 1, 1 plus some multiple of this black vector v. Okay, so let's write that here. So the line is all xy that can be written of the form minus 1, 1 plus t, this vector. Okay, and this is one of the new forms of the equation of a line. This is called the vector form. Okay, so now we have 1, 2, 3, 4 different forms. I mean, what's going to be important for us in this section and the next is really this form, but also what's called parametric form. So let me erase some of, I'll erase those two. This one is important because I'm going to come back to it, but the final form is called the parametric form, and I will write these more generally in a moment. I'm just writing them for this example. Well, the parametric form we literally get by looking at the vector form. We look at each component. It says that x is minus 1 plus 3t. It says that y is 1 plus 2t. And here, t is referred to as the parameter. And this is, you know, sometimes we'll think about t as being time, but that's referred to the parameter here. This is the parametric form. Okay, so if we let t, go from minus infinity to infinity, we fill out the whole line, and similarly, writing it in this form. Now, the general form, and I have written this in terms of R3, but all you have to do to get the statement for R2, which we just saw in that example, is just remove the third coordinate in this statement. But the vector form of a line in R3, we have x, y, z. Well, we have some point that's on the line, okay? Then plus t, ABC, where this is a vector that's parallel to the line. And similarly, if we want the parametric form, we have, let's see, x is x0 plus ta. We have y is y0 plus tb, and we have z is z0 plus tc. And in both of these, t is just goes between minus infinity to infinity to fill out the entire line. Okay, now let's do an example that will be, our first example is just literally going to be use this formula, and then we will get into some more interesting ones. Okay, we want to find an equation of the line. Here's our point, and here is the vector it's parallel to. Well, like I mentioned, this is just straight. Can we apply this formula to a specific example? It goes through this point, and then it's parallel to this vector. And maybe for this one, I will also do the parametric form, but I won't do this every time. We could write x is 5 minus t. We could write y is 2 plus t. And we could write z is 2t. Okay, this is the parametric form. Okay, both of these are giving the exact same line. Here are two more examples where we're going to find the equation of a line. The first, we are given 1.73 minus 1 on the line, and we're told the line is parallel to this line. Well, okay, this is not much different than the first. This given line here is parallel to this 12, 3 minus 5. And so we're trying to be parallel also to 12, 3 minus 5. We want the line through this point and parallel to this same vector. And we have this in vector form. We want this point and then plus t, this vector. Oh, just like this, okay? Just slightly different than the first example. Now, okay, this one is very nice because this is kind of like the first one that we saw in R2, where I started with slope intercept, point slope like this, okay? We have 2 points in R3, and we want an equation of the line that connects them. Okay, well, I'll label, let's say P and Q. We know, just like in the very first example, we take this vector, which is, well, I'll do it this way. We have minus 3. 1 minus 2 is minus 1, and then minus 1. This vector is parallel to the line, and so we can take xyz equals 5 to 0 plus t times minus 3 minus 1 minus 1. And this gives us a vector form for this line. Now, what do we notice here? In this example, maybe I will switch colors for this, that when t equals 0, we get the point P, and when t equals 1, we get the point Q. And so in particular, one thing that we see is, and this will be a comment, if we wanted the line segment between P and Q, this has equation, well, it's the exact same thing. X, Y, Z is 5, 2, 0 plus t minus 3 minus 1 minus 1, but t ranges between 0 and 1, whereas the entire line, we take t from minus infinity to infinity. So that's just a comment. And I will also say, before I erase and do more things, this is not the only way to do it. This is not unique at all. I could have done this point minus this point, and then I would have a positive 3, 1, 1, and this would be fine too. Okay, and to get the line, I could have also, instead of putting 5, 2, 0 here, I could put this point here and use, well, either minus 3, minus 1, or 3, 1, 1. There's not only one equation of a line in this form. Okay, I'd like to go back to our first example because it's going to move us into talking about planes in our 3. It was a line in our 2, and I left this standard form of the equation of the line on the board down here a little bit longer because I said I was going to use it. Well, I'm actually not using it until now, but this standard form of this line, this gave a line that was parallel to this vector, right? If you remember, you can look back at your notes and see this, or back the video up if you forgot. Okay, now this is going to get cool really soon. This is in R2. And being parallel to this vector 3, 2 is equivalent to being perpendicular to 2 minus 3, right? Well, where do you see 2 minus 3 here? We look here and we look here. We see 2 minus 3, and this is the x and this is the y. This is in front of the x, this is in front of the y. Okay, and this is not by chance. So it was important that the dimensions worked out, because if you look at lines in R3, you can't really make a similar statement. So what we had was we had a line in R2 here, and this type of equation gave something that was, gave something that was perpendicular to what we read off from the equation, right? And what we're trying to move to, this generalizes to, I will say, a plane in R3. And more generally, I will say hyperplane in Rn, although I'm really just going to be working with planes in R3. But before I get into this any further, let me just talk about dimensions. This is dimension 1 sitting inside something of dimension 2. And we have this. If you look at the standard form of the equation of this line, you can read off a vector it's perpendicular to. And here, a plane in R2 is dimension 2 sitting inside something of dimension 3. And we will also, what is a hyperplane? Well, it's dimension n minus 1 sitting inside something of dimension n. And this is really what this statement will generalize to. But let's talk about planes in R3. And guess what? The standard form of a plane in R3, it looks almost like this. And it's going to be something very similar, where we can read off, just by looking at the equation of a plane in R3, we can read off a vector that is perpendicular to the entire plane. What is the equation of a plane in R3? Well, we have A, x minus x0 plus B, y minus y0 plus c z minus z0 equals 0, where x0, y0, z0 is a point on the plane, and this vector, I will write it this way, n, which is a, b, c. This is called the normal vector, and this is perpendicular to the plane. And what do I mean by that? Well, what I mean by writing this, it says that a point x, y, z is on the plane provided this equation holds. And, well, there's another way to think about this. So maybe I will make some notes right now as we think about this before we do some examples. The first note that I will make, this is really dot product. We are given P, x0, y0, z0 on the plane. And then, well, this point Q, which is x, y, z, is on the plane provided, well, if we take V, which is this vector is perpendicular to this n. And that's exactly what we see here, because look, this equation is exactly saying that n dot v, is 0. That's what this equation says exactly. Now, my other note, we can rewrite this. So we can rewrite the equation as ax plus by plus cz plus d equals 0, where d is, well, let's see what this would be. It would be minus ax0 minus by0 minus cz0. And we still have that this is perpendicular to the plane, right? And this is what, well, this sometimes is called the standard form of the equation of a plane, and this is what generalizes what I had up here for the standard form of a line. And you can read off a vector that's perpendicular to the line, and look, you can read off A, B, C is perpendicular to the plane, okay? It's just the next dimension up, okay, of the same statement. And as I mentioned, you could make a similar statement about a hyperplane in Rn. I just want to show an example of this normal vector with the plane graphed in a way that I could not do on a whiteboard. So this is Maple, and if you look here, the way that I am feeding in a plane or telling Maple I have a plane, this first triple is a point on the plane. 2, 0, 6 is a point on my plane. And then this is the normal vector, 1, minus 1, 4. And, well, this will be the first example I do of writing the equation. But if I look, okay, now, what you see is graph the plane and then it graphs the normal vector with it. And you see, if you think about geometrically this plane and then the normal vector, you see the way that it meets, the normal vector is perpendicular to the plane. Okay. Well, here are two examples. This first one is just straight apply the formula for the equation of a plane given a point and a normal vector. And the second one is a little different. The second one came off old Calc 2 final, so it's very good for us to practice. Well, here we're given a point, we're given a normal vector, and so we know the equation of the plane will be, it'll be 1 x minus 2 minus 1 y minus 0, and then plus 4z minus 6 equals 0. This is a perfectly fine equation. You can leave it like this. It looks nice like this because you see the point and you see the normal vector, but if you wanted to write it in standard form, for instance, we could multiply out and we get x minus y plus 4z minus 26 equals 0. So this bottom one is the exact same, and it's an equation for the exact same plane, it's just in different form, standard form. Okay? Now, this one we're back to finding the equation of a line, but there's something about a plane in it. So let's read the question. We want the line to contain this point, minus a half, 1 minus a half, and we want the line to be perpendicular to this plane. Okay, well, we can look at this equation of the plane, and immediately we see the plane has normal vector n, which is 1 minus 2, 1. Okay? And if our line is going to be perpendicular to the plane, it means that this vector must be parallel to the line. So the line should be parallel to this vector. Okay, and we have a point. So now we have a vector parallel to the line, and we have a point on the line. So we know in vector form, oh, vector equation, very nice. We have xyz equals, it's the point minus a half, 1 minus a half, and then plus t 1 minus 2, 1. Okay? This would be a vector equation for this line. Let's do this example where we're looking for the x, y, and z intercepts of the plane that contains this point 4, minus 1, minus 3, and has normal vector minus 1, 2, 1. Well, immediately we can write an equation of this plane. We have a point. We have a normal vector, and this is exactly what we need for an equation. So it says here, minus 1, x minus 4 plus 2 is going to be y minus 1, which is y plus 1. And then here, plus 1, we have z minus 3, which is z plus 3 equals 0. This is an equation for our plane. But, well, the x, y, z intercepts, well, the x-intercept, for example, has y and z 0. The y-intercept has x and z 0. And the z-intercept has x and y equal to 0. So it's going to be a little bit easier to solve if I rewrite the equation of the plane. So we have minus x plus 4 plus 2y plus 2 plus z plus 3 equals 0. Or if I bring this, let's see, 4 plus 2 plus 3, this 9 to the other side, I get minus x plus 2y plus z is negative 9. And for example, like we were just discussing, just looking here, you can read off the normal vector, minus 1, 2, 1. Okay, very nice. But now let's move on to the intercepts. So we want the point on the plane such that y and z are 0, and we can easily solve for x here. This would be for the x-intercept. We have minus x equals minus 9. X equals 9. The point on the plane is 9, 0, 0. Okay? Now the y-intercept, x and z are both 0. The y-intercept, we have 2y equals minus 9. Y is negative 9 over 2, and the point on the plane is 0. Negative 9 over 2, 0. And finally, the z-intercept, x and y are 0. Immediately, z is negative 9, and the point on the graph is 0, 0, negative 9. So these are our three intercepts, the x-intercept, y-intercept, and z-intercept for this plane. Let's look at this example, which is asking us to determine points of intersection for a plane and a line. And pardon my art skills, but I've tried to illustrate the three things that can happen when you have a plane and a line. This is supposed to depict the line is fully inside the plane, and then they would intersect in the entire line's worth, okay? And this one, this is supposed to be illustrating the fact that the plane and the line are parallel, but the line is not inside the plane, okay? Then they would have no points of intersection. And finally, you have the other thing that can happen, which if you're not sitting inside the plane or parallel but not sitting inside the plane, the plane and the line will intersect in precisely one point. So these are what can happen, and we need to address this here. We want to determine this point if they so happen to intersect like this, or the whole line's worth, or the answer would be no solutions if there's nothing. So how do we do this? Well, you see, let's use this and get parametric. The line, we know that x is 5 plus 3t. We know that y is 2 plus t. And we know that z is 0 plus t. So what we can do is we can just substitute into the equation for the plane and then solve for t. If we can solve for t, then we will have the intersection. Okay, so let's do this. We get 2x minus 3y plus z equals 8. And now we try to solve for t. 10 plus 5t, multiply 6t minus 6 minus 3t plus t equals 8. And now we have 6 minus 3 plus 1. We have 4t. This is 10 minus 6. Subtract. We get 4t is 4. We get t equals 1. So in fact, we do have a point of intersection. And with this here, this parameterization, it happens with t equals 1. And so all we need to do is just put t equals 1 here, and we will find the point of intersection. The point of intersection is x, y, z equals 5, 2, 0 plus 1 times 3, 1, 1, which is 8, 3, 1. Okay? So this is my point of intersection right here. Let's close today on discussing this example, which is something that we really want to do. We are given 3 points and we want to find an equation of the plane. Now, let's just back up for a moment. If we have 2 points in Rn, let's say distinct, meaning they're not equal to each other, then we get a unique line. Okay? If we have 3 points in Rn and I need them to be not collinear, this means they are not all 3 along the same line, then we get a plane. So we have 3 points in R3, and this is very natural to ask the equation of the plane containing them. Well, the problem is, if we stare at these 3 points, we don't have a normal vector to the plane. Well, what do we know? So what do we know in this case? In this example, let's say. And let me label some points. I'll label this P, Q, and R. We know vector PQ, which is 1, 2, 3 minus 0, 0, 0. It's just this vector, 1, 2, 3. And we know vector R, which is minus 1, 5, 3, minus 0, 0, 0. It's just minus 1, 5, 3. Both of these vectors sit in the plane. So what we need, in order to get a normal vector, we need, let me call this V, and I'll call this W. We need N to be perpendicular to both V and W. And if we can find a vector that's perpendicular to both of these, we have a normal vector for the plane. Well, we have 3 different points we could choose from as our point. We have normal vector, we have point, we have the equation. But the question of, given 2 vectors in R3, how do you find a vector that's perpendicular to them both? Well, we don't have yet. And so let me just end by saying this is next time. So this is why the full question of finding an equation of a plane we cannot address today. We will come back next time and address this. I will just say we're going to use something called the cross product. We will see V cross W is perpendicular to both. Both V and W. And this is what we can use as a normal vector to the plane.